Hello, everyone. Welcome back to AIQuantEasy, from zero to hero. Recall in the previous episode, we trained a simple supervised learning model and use it to make a prediction of good days to buy shares. This is the code that we used in the previous episode. I just made a minor change. So the change is that instead of load decades of records, we just load the 5 most recent years of daily record for SPY. The reason for that is I want to visualize the records in the testing dataset with the predicted label in order to analyze the performance of the model. If we have too many records in the testing dataset, the visualization will not look good. So that's why I just reduce the amount of data we load to analysis. Okay, let's just run this code. Load the data, then derive indicators. We skip the stock visualization part and labeling the data and visualize the label data. Then train the supervised learning model, more particularly the random forest classifier. We train on 80% of the records and then use it to make prediction for each record in the 20% of the testing data set. We run it. So we got 70.72% of accuracy rate. So does this mean this performance of the model really good? Actually, we cannot say that because we cannot get much information about the performance of a model purely from accuracy rate. Okay, what we need to do is we need to calculate another measure, which is called confusion matrix. So this confusion matrix will give us way more insight on the performance of the supervised learning model that we train. So in order to calculate the confusion matrix, so here we import confusion matrix, this class, from scikit-learn.metrics, right? So in the previous episode, we just imported this accuracy score. So now we import this confusion matrix. Then we just calculate the confusion matrix based on the predicted labels. So these are the labels that are predicted by the model. And these are the labels that we really assigned based on our labeling strategy to each of the record in the testing data set. So we basically compare what the model predicted and what are the real label values. Then we get this confusion matrix, right? So we will run this to show the matrix. Then we will see how we interpreted this matrix. Okay, so here we get this 2x2 confusion matrix. So what does this mean? Okay, let's first look at the first row of this matrix. The first row represents what is the model predicted as 0. The second row represents what the model predicted as 1. 1, remember that 1 represents a good day. 0 represents not a good day, right? So again, the first row represents what the model predicted as 0. And the first column represented what the model predicted as 1. Okay, how about the first column? The first column represents those records in the testing data set with the label value to be 0. So those are real 0. The first column represents a real 0, okay? Those records in the testing data set with label value to be 0. So those are real zeros. The second column represents those testing records with label value to be 1. So those are real ones. So in short, the first row represents what is the model predicted as 0. The second row represents what the model predicted as 1. The first column represents real 0, and the second column represents real 1. Okay? So the first value, this value, what I highlighted here, represent that these are the number of testing records that the model predicted as 0. And also they are real zeros. So these are the values represent the number of testing records that the model correctly predicted as 0. Okay, the model predicted as 0 and they are real 0. So the second number here represent the number of testing records that the model predicted as 0, but they are actually 1s. Okay, so in other words, this number represents the false selective. The model predicted as 0, but they are actually 1s. Okay, so we have this much of testing records. The model mistakenly predicted as 0. Their actual label values are 1. Okay, so this number represent what the model predicted as 1, but they are actually 0. Okay, so these are called false positive. Okay, so the model mistakenly predicted as 1, but they are actually 0. So in other words, there are 11 records in the testing data set that the model predicted as 1, but they're actual zeros. This value represented the model predicted as 1s, and they are the records that really have label value to be 1. So this is called true positive. This is called false positive. Okay, this is called false negative. This is called true negative. Okay, so look at this diagonal line. So 362 and 10. So the numbers on the diagonal lines are the ones that are correctly predicted. Okay, so this confusion matrix gives us much more information about the performance of the model than just this accuracy rate, right? But just look at this accuracy rate, 70.72%. Wow, that's way more than 50%. Seems it's represent a good performed model, right? Should we follow the model to buy shares? Actually, no, we shouldn't do that because this confusion matrix just show us like the performance is not good at all. Just look at the second column, right? There are totally 143 plus 10 records. They are real ones. But among these 153 real ones, the model only predicted 10 as ones. The rest of the mistakenly predicted as what? As 0. So that means what? From 153 real ones, the model only predicted 10 of them as ones. So the recall, this is called recall level, is very low. The recall level is very low. Okay. So in other words, according to our definition, they're supposed to have 153 days, which are good days, to enter into positions, right? But among these 153 good days to enter into positions, the model only predicted 10 days, right? So the recall level is very small. So in other words, you may miss a lot of trading opportunities by following this model, right? So there are 153 good days to purchase, but you only, based on our definition, okay? But you only, the model only get 10 of them, right? So you will miss a lot of those trading opportunities. Okay, so also this number represents that there are 11 days, actually they are not good day to enter positions, but the model predicted them as good days, right? So also look at the accuracy rate. Seems it's quite high, but actually this confusion matrix tell us that this model is not a good model at all, right? So we want to basically visualize the predicted value with the test records to say, what are those days that they predicted as a good days, right? And from the visualization perspective, we want to say it's a good model or not. So here, after we generate the confusion matrix, so here basically we just want to visualize the daily records on a testing data set with predicted label, right? So we call this function ones and the zeros that we defined earlier when we basically visualize the label data, right? So we define the ones to generate the signals for the days with uh, label to be one, right? And we use these zeros to generate the signals with the days label to be zero. So here, we just call these two methods. So here we just call these two methods, right, to generate the signals for those testing records that is a model predicted as one, right? And we call these zeros to generate the signals for those testing data records that is a model predicted as zero, right? And then we just trying to plot these two list of signals with the price and the volume information of the days in this testing data set. Okay, so let's run it and see what we get. Okay, so this is what we get. You see, for majority of those days, the model predicted as zero. Okay, so that's why you see so many red down arrows, right? And just a very few of them, actually the model predicted as what? As ones, which are represented by these up blue arrows. So the recall level is very low for this model. Again, this confusion matrix tell us that this simple um, supervised learning model is not work that good. We shouldn't follow it for trading, right? So, but looks like it happens that this this model uh, somehow picked those uh, the bottom of the last year. Okay, they pick the bottom prices, bottom days, right? For last year, for the recent year, right? But again, I believe this is just a coincidence, right? So because we designed the model not predicting the bottom or peak, right? We did design this model to predict what is a good day to gain 5% profit instead of 2% loss, right? But from the result, seems it correctly picked the bottoms of this recent year, right? But again, I just viewed it as a coincidence, right? So this not necessarily mean that this model can find the bottom of the market of the stock price. This pure coincidence, right? So definitely, I mean, this simple strategy to make a prediction on the stock data, it's not working well, okay? Um, you may say, how about we change to other supervised learning model? Actually, in order to do so, it's very simple. So here, we can try different other supervised learning models instead of random forest, right? So for example, we can try k nearest neighbors, right? K nearest neighbors is another supervised learning models. Basically, in order to predict a testing record, right? Uh, we find it's a key um, nearest labor from the training data set towards this test record, right? And use those k nearest neighbor situations to label this testing record. So the key could be three. That means we use three closest labels to label the current testing record. Or the key equal to 5. That means we use 5 nearest labels to label the current testing record. Or if the key equal to 7, that means we use 7 nearest labels from the training data set to label the current testing record, right? So that's key nearest neighbor. We can also directly use decision tree. This random forest basically is a symbol of multiple trees, right? So when we create this random forest classifier here, we specify the number of estimators to be 100. That means what? We use 100. We will build 100 decision trees, right? So it's a ensemble of decision trees. If we directly use a decision tree, that means we just build one decision tree to make the prediction, right? So in order to use different type of supervised learning model, actually, it's very easy, right? We just use the nearest neighbor and the decision tree as an example. You can just use other models in the same manner, right? Like support vector machine or logistic regression and so on, right? So for example, I want to use a decision tree instead of random forest. So what I would do is just here change one line of code. So instead of generate an instance of random forest classifier, I just commented this out. I generate an instance of decision tree by using this line, right? Of course, in order to use this, you have to import the tree from scikit-learn, right? Okay, so we just generate an instance of decision tree classifier instead of random forest. Then the rest is the same. Then we train this instance on the training data. And then after training, we use it to make a prediction for each record in a testing data set. So the rest is the same, right? So let's just run this decision tree to say what performance they may give to us, right? So recall that for random forest, we have accuracy rate to be 70.72%. Then we further print out the confusion matrix. It's like this, right? So we run, if we change to decision tree, then the accuracy rate reduce a lot. It become less than 50%, right? So let's see for confusion matrix. For confusion matrix, basically, again, the recall level actually increased a little bit, but this model mistakenly predicted ones for 197 records in the testing data set. So this is false positive. The false positive increased a lot, right? And this is false selective. False selective reduce a lot, right? But still not looks good, right? Still looks no good because for those ones, for those zeros, actually 197 of them should be zeros, but we predict as one. What does that mean? That means if you follow this model, there are 197 days actually. You expect to gain 5% increase, but actually you may encounter at least a 2% loss, right? So there are so many false positive, so which does not work good. Even worse than random forest. So typically, decision tree has a worse performance than random forest because random forest is a ensemble approach. They will use a lot of trees to make the decision, but decision tree just use one single tree, so it's easy to have overfitting or underfitting issues. So basically, let's run the visualization based on decision tree. So you can say that we have way more ones be predicted by the model, right? But the false positive again increase a lot, right? So for these things, I think most of these days shouldn't be one, but they predict as ones. So that's also depends on what are the training data that we use? For this case, we just use the the past 4 years as a training data set, right? So past 4 years, if I remember correctly, for SPY, I think most of the time they have uptrend. So that's why maybe they predict all these like as ones because they kind of like V-shaped type of recovery to uptrend one after a downtrend, right? In the past, maybe that's the case. So here they thought maybe this is the same case, but actually last year we have a big down, right? Continuous down. Anyway, so the performance is no good at all. So let's just try nearest neighbor to see what we get. So we will try 3 nearest neighbor, k equal to 3. So in other words, again, in order to make a prediction for a testing record, right? We first find the 3 nearest neighbor from the training data set. Then based on that 3 nearest neighbors labels, we come up with a label for this testing data set, testing record. Okay, so let's generate instance for the 3 nearest neighbor and train it and then apply it to test records. Okay, we got like 57% accuracy rate. From accuracy rate perspective, it's slightly better than decision tree. Again, this accuracy rate does not provide enough information for us to look into the performance of the model. We have to calculate the confusion matrix. Okay, so we got this confusion matrix. So again, it's kind of like more ones predicted, recall level improved compared with random forest. But again, so this false positive still too many, right? Too many than acceptable. So let's just visualize the predicted values. So again, we catch those real ones somewhere here, some of these, but we also had quite some false positives like this, maybe on the peak, right? Again, the nearest neighbor will make a prediction for example, for a day like here by looking for the 3 nearest neighbors in the training data set. But in the training data set, because the major trend is up, maybe something like this, something like a down, then going up, most likely they will continue to go up in the training data set, right? That's why they predict all these as ones. But actually for this year, it's quite different, right? So they have a long downtrend. So that's why you see the stock market data is very complex, right? This simple supervised learning model will not work well for making predictions because, I mean, although like random forest models typically works very well for typical simpler data set, right? Like sales market prediction or, you know, customer churn prediction or something like that. So those are typically working well because those data, the pattern embedded in those data sets are pretty simple, straightforward. But for stock data, because it's so complex, right? There are so many hidden factors drives the stock data. And so even for the days which have similar price, volume, relative price compared to moving averages, similar volume information, similar indicator values, they may have totally different following directions, right? So one could be up, the other similar days could be after that day could go down, right? So all possibles, right? So stock data is very complex. That's why we want to take these challenges, right? Trying to apply different AI technologies to analyze the stock data. right? So here we just show you how we can use simple supervised learning to make some predictions, right? And then definitely, I mean, this model does not work well, right? So definitely we have to design much more sophisticated strategies by using AI technology, right? So we'll talk about that in the following episode. Just stay tuned.